Have you ever wondered how a mistake simple enough to cost you a few points on a physics test could end up recorded as the most expensive error of its kind in history? In this video, you'll learn why the loss of NASA's Mars Climate Orbiter is still taught in engineering and physics classes around the world, how the agency lost two separate spacecraft at Mars within 11 weeks of one another, and what an official investigation concluded about the safeguards that were supposed to prevent it. You'll hear why a signal that went quiet just 49 seconds early told engineers the mission was already over, how a warning raised in the final days before arrival went unresolved, and how a probe that flew flawlessly across more than 400 million miles of space was destroyed within minutes of reaching its destination. And behind all of it sits a single question. How does a spacecraft worth $125 million end up lost because one team measured in pounds while another read newtons? NASA's Mars Climate Orbiter was lost because two engineering teams never reconciled the units they were working in. One team's software reported a set of measurements in pounds. The system receiving those measurements read them as newtons. The discrepancy went undetected, and a spacecraft that cost $125 million was destroyed on arrival at Mars. The orbiter was launched on December 11, 1998, from Cape Canaveral, Florida, aboard a Delta II rocket. Its assignment was routine for a Mars mission: to study the planet's weather, track its dust and water vapor, and serve as a radio relay for a second spacecraft, the Mars Polar Lander, that was following close behind. For 9.5 months, the orbiter performed as designed. It crossed 669 million kilometers, roughly 416 million miles, and arrived at Mars very close to its intended position. On September 7, 1999, it returned a single photograph of the planet. That image would be the only one it ever sent. On September 23, 1999, at 9 hours 0 minutes and 46 seconds Greenwich time, the orbiter fired its engine to enter orbit around Mars. About 4 minutes later, it passed behind the planet and its signal cut out. A loss of signal at that point was expected, since every spacecraft goes silent when a planet blocks its line of sight to Earth. But the signal stopped 49 seconds earlier than the calculations predicted. The early loss of contact meant the spacecraft was too low. It approached Mars on a path that brought it within about 57 kilometers or 35 miles of the surface. The lowest altitude it was built to survive was roughly 80 kilometers. At 57, it entered air far denser than it was designed to withstand, and was either torn apart in the atmosphere or deflected back into orbit around the Sun. NASA was never able to determine which. The signal did not return. The cause traces back to how the mission was divided. The spacecraft was built by Lockheed Martin in Colorado, and its navigation was managed by NASA's Jet Propulsion Laboratory in California. To keep the orbiter on course, ground software calculated the small forces produced by its thrusters and passed those figures to the navigation system. The software Lockheed Martin supplied reported those forces in pound-force seconds, a unit from the English system. The NASA navigation software expected Newton seconds, the metric unit, which the contract between the two organizations specified. The conversion between them was never applied. 1 pound of force equals about 4.45 newtons. Every thruster measurement the navigation team received was therefore off by roughly that factor, consistently understating how hard the spacecraft was being pushed. Over millions of miles, those small errors accumulated in the same direction, bending the flight path steadily closer to the planet than the ground team could observe. The hardware functioned correctly throughout. The spacecraft was lost to a mismatch in units, an error of the kind ordinarily corrected in an introductory physics course. The problem was visible before the final maneuver. In the days leading up to orbit insertion, the navigation team's altitude estimates kept moving lower from an initial range of about 150 to 170 kilometers down to roughly 110 kilometers in the final 24 hours. The concern was raised. It was not resolved before the spacecraft reached Mars. NASA opened a formal investigation. On October 6, 1999, it appointed Arthur Stevenson, director of its Marshall Space Flight Center, to lead the review board, and the board released its report on November 10, 1999. Stevenson identified the root cause as the failed translation of English units into metric units in a segment of ground-based navigation software. Edward Weiler, NASA's Associate Administrator for Space Science, addressed the larger failure directly. The problem here was not the error, he said. It was the failure of NASA's systems engineering and the checks and balances in our processes to detect the error. That's why we lost the spacecraft. The mistake itself was the kind engineers anticipate. The failure was that a $125 million mission had no functioning check that caught it. Richard Cook, who managed NASA's Mars projects at the time, later told Wired that the unit's error had become the standard textbook example, and that everyone involved was surprised it had gone unnoticed. The $125 million figure covers the orbiter alone. It was one of two spacecraft in a program called Mars Surveyor 98. Counting its sister ship, the launches, and mission operations, the full program cost $327.6 million, of which about $193 million went to building the spacecraft, $92 million to launch, and $43 million to operations. Adjusted for inflation, that total exceeds $586 million in current terms. The second spacecraft was also lost. On December 3, 1999, weeks after the orbiter's failure, the Mars Polar Lander reached Mars and fell silent, most likely because its engine shut down prematurely. The cause was different, but the outcome was the same, and NASA lost both halves of Mars Surveyor 98 within 11 weeks. Historically, about two-thirds of all spacecraft sent to Mars had failed before completing their missions, which is the reason such missions depend on rigorous, repeated verification. Under those conditions, a unit's mismatch that passes through review reflects a process not strong enough for the task. The scientific work the orbiter was meant to do was eventually carried out. In 2005, NASA launched the Mars Reconnaissance Orbiter, which accomplished most of the original mission's objectives, though years later and at considerably greater cost. The Mars Climate Orbiter is now recorded by Guinness World Records as the most expensive metric-to-imperial conversion error ever made, and it appears in engineering and physics courses as a standard example. Describing it only as a unit's error, however, understates the finding of the investigation. The unit mismatch was the trigger. The mission was lost because, on a program where detecting such mistakes was the central task, the systems meant to catch it did not.